9 o'clock, and so why don't we get started? I'd like to thank you all very much indeed for joining me today, and some of you I know will hear this later after this has been recorded and you listen to it in that form. So thank you for coming and listening to this live today, and I hope that we'll have a nice discussion and some interesting questions at the end as well. So what I'm going to do is I'm going to spend the next 40 minutes or so, I hope, describing to you in this first session of a webinar on our new product that describes the analysis of simple mixtures. Okay, so mixtures are everywhere. They're absolutely everywhere, and their assay is hugely important. And using NMR has got a number of very, very exciting possibilities. Any analysis of mixtures is going to be somewhat complicated by definition, and what we hope we've developed, and I can convince you of, is a very nice way of tackling that mixtures analysis issue. So we've got quite a lot of material on our website, and this is it over here, and once you get the PDF version of this, you can double click this and it'll take you straight to the website page, and there's, as I say, a lot of information over there. I'm going to be giving two webinars, as you know. The first of these today is going to be rather high level and overview, and what I'll do in the second webinar is to really dig into the detail and show you exactly how all of these claims and promises and bits of information that I'm giving you today and glossing over somewhat can be brought into reality, and you can use these yourself in your own lab. So the area of I need to do that. So mixtures and various forms of these have been in the news quite a bit lately, so let me set the stage in that way. So we've seen articles on the fact that herbal supplements aren't what you think they are, and we've seen lots of talks from people in the NMR community about this as well, whether they're working with the large high-field instruments or whether they're working with the smaller benchtop magnets. Recently there's also been a huge debate over the fact that the EU regulators call for generic drug suspensions from a particular producer, and this has had a huge impact on certain big name sellers in the US. So a massive thing. They found that huge numbers of generic drugs really weren't what they said they were on the packaging. And the last little bit here is more sensationalist. There's been these hard questions over the litany of forensic failures at US labs, and lots been written about that. So very much a topical subject, I'd have to say, and I think we're coming at this with at a really good time, and I think at a time when people who aren't worried about this, who aren't concerned about this, really should be. So I hope that I can convince you of that today. So why the interest in mixtures? So it really, I think, largely comes down to quality assurance, if you want sort of one name under which to put all of these various interests. And there are very, very many number of diverse reasons why mixtures analysis might be interesting to you. So if you're living in the world of fine chemicals, then you probably want to deliver with your product some sort of certificate of analysis. The fine chemical might be something that you buy out of a catalog, or it might be a drug substance, an active pharmaceutical ingredient, API. All of these need to come with very clear certificates of analysis that say that what's in the material is what they say it is, first of all, that it's genuine, and secondly, it's quite often the fact that certain impurities are known and allowed, but their levels have to be controlled and have to be kept to within certain guidelines. And so that certificate of analysis is a very important document to accompany a material. Forensic examination is a huge area which is very, very tightly regulated, as you'd imagine, and they make very, very strong use of purity determination, and and such like. This is obviously for use in the courts. Consumer products, foods, nutraceuticals, wines, beers, anything you'd like to put here. These are all coming under far greater scrutiny than has ever been the case in the past. People traditionally have just put anything in a bag and put a name on it and said what's in there. But we all know from lots of tests that have been done that this is because it's a largely unregulated area, it's open to huge abuse, and a lot of the material that's coming in and being sold to customers is not what it says it is, and it can be quite dangerous. So the correct and proper labeling and description of materials is hugely important. And there are government guidelines and regulations around this area, and they're only getting stronger as time goes by, because people realize that if you give people open book in this area, then anything can go into these packages, and they can be dangerous. Okay, so what sort of approaches can we use what sort of approaches can we take using NMR when it comes to mixed analysis? I've broken this down very, very roughly into two. The first of these is the targeted analysis approach, where one tries to find individual NMR resonances that belong to, are attributable to a particular component of the mixture, and then you derive some sort of mathematical way in which to convert that interval, if you like, into some form of a quantification. The second approach is by using chemometrics and things like PLS. Math modeling is hugely successful and useful in many, many cases. I'm going to say absolutely nothing about the second of these approaches, chemometrics. I'm going to focus all my attention on targeted analysis. So what's going on here when we're doing targeted analysis? The fundamentals are that we really need to identify a unique component based on one or more peaks, a multiplet or spectral range in the mixture spectrum. That's really the heart of it. And for that peak or that multiplet, we're going to determine an area, and the fundamental property that we always try to get out is this sort of normalized area, this area divided by the number of nuclides, this AI over double N. So you'll see this many, many times today, and if you do a bit of reading in this area, you'll see it huge numbers of times. It's the fundamental unit of NMR quantification. We then need to be able to relate that area, that normalized area, into some sort of quantitation unit, and that requires some sort of formula, and I'll say a little bit more about that in a minute. So that's that there, giving some accent to that need for a way to convert that. This equation that I'm showing at the bottom is a really fundamental one for all NMR concentration determinations. It simply says that the concentration of a component in a mixture, of any component in a mixture for a specific measurement, is proportional to this normalized area, this AI over NM. And the value K is some sort of proportionality constant or some sort of spectrometer specific number that allows you to generate an equation that links concentration with area. So we're going to see this many times today. It's absolutely fundamental to concentration determination. But as you are all aware, I'm sure, that the brilliant thing about NMR is the fact that all the compounds, all the components present in the mixture will share the same proportionality here. So you don't have to generate a different K value, if you like, for each component. Once you've got this equation established, you can work out the concentration of any and every component in the mixture without any fuss or bother. It's absolutely pivotal. This is the real strength of NMR. Okay, so what's the basic philosophy behind the simple mixtures analysis, this SMA that we're talking about today? So we want to build something, or we've wanted to build something that's versatile, which is to say that it's not going to be restricted to one particular analysis. It's going to be applicable to hopefully almost any analysis really. And to achieve this, we've made it fully user configurable, and I call this a design and deploy approach. So at some point in time, you or a colleague has to spend some time designing an experiment, and I'm not going to say a lot about that today, but certainly in the second webinar I'm going to say huge amounts about that, because that's a vital step in the whole process. If you don't have an experiment designed, then you have no place to start. Okay, let's assume you've done that, you've done your hard work, and what you can then do, of course, is you can share those experiments with your co-workers, or you could even sell those on if you wanted, I suppose. And what underpins all of this really is a very nice workflow in the software that allows you to build confidence in each of your analyses. And I'll be showing you that today as well. Now, everything I'll be doing today is in an interactive fashion, but you can use SMA in partially or fully automatic operation, as I'll hint at the end. And we have some flexible reporting tools available to you at the end of the whole game. So we come to this design and deploy approach. What have we got here? Well, one approach to doing analysis is to have a black box theory, where you have your black box and you've got some input and some output comes out the other end, and you don't allow anyone to know what's happening inside this black box. But this is really what we want to avoid, because we want to make everything totally transparent and configurable. So to do that, we have a paradigm where we maintain libraries. So a library is simply a place where you can store experiments. Okay, so I'm just giving you a bit of terminology here. What's an experiment? So each experiment, in fact, is a specific analysis. As I go through the examples and the demos, you'll see that may become a little bit more clear. So you design an experiment and you put it in a library. And you may want to share that with others who may want to put it in their libraries as well. Now, the whole big deal here is, how you specify exactly how the extracted NMR data is tailored to your specific QNMR task. So what we're going to do here is we're going to allow you to specify particular signals or spectral regions, and the areas will be determined when you do the analysis. And those areas will be pushed into a mathematical expression that you will specify, and those in turn will lead to some sort of QNMR parameter like concentration or whatever it is. You'll see some examples of that. Okay, so this is really the heart of it. And once you've generated the experiment, that just sits as a file and sits in your library there. It's a pull-down item. And any time that you or a co-worker wants to perform it, they simply pull it down and put in any information that's required and click one button and off they go. It's done. So that's the big one that I'm going to be really focusing on a lot in the second webinar and really glossing over today. So the equations that are involved in converting areas into concentrations and so on are these types of textbook equations that you'll see all the time. Mole ratios are this type of thing. I is the integral, N is the number of nuclides in all of these equations. I've put the textbook equation in the middle, and on the right I've put the type of equation that you'll use when you specify this inside SMA. So you can see that they're not hugely horrible equations, and you just have to get to know them a little bit. And we provide lots of help in that area. Okay, so might SMA be useful to you? Well, yes, I hope so. And if you're interested in repeatedly analyzing things like drug substances for release, if you're interested in compound purity determinations, if you want to quantitate components of biological fluids, fermentation broths, analysis of components of wines, oils, so on and so forth. The list is endless, as I say, and I've just put a few down here because they relate a little bit to the examples I'm going to show you. Now, the big elephant in the corner that people always talk about when it comes to this targeted approach is, well, what do you do when signals overlap? Okay, are you really stuck if two signals are overlapped? Well, not necessarily. And I'd advocate that a targeted approach is really a very nice, satisfying, and intellectually pleasing approach, one where you can actually see exactly what's being done by looking at the spectrum. And so it's one that I think I would like to use as a default. And the number of ways in which to extend the standard analysis. So if you think of that as the standard 1D proton spectrum, and that's what everyone, I guess, or most people will acquire as default. There are many other things that you can do to make this still possible in cases where you do have extensive overlap. So the first of these is to use more than one experiment per sample. So one thing that's possible with SMA, which is quite unique, is capability to deal with more than one experiment in a single quantification experiment. So you might say that I'm looking for the area in this region from experiment 1, which might be a proton spectrum, and that might be mixed up with the area from a peak that's been generated in a 1D toxicity spectrum, which might be in experiment 2. And so you can address all of these areas in different experiments. So you can have as many experiments as you wish, in principle, which may be NMR experiments, or there may be experiments that are being processed differently as well. So that's really quite important. The second is that we have full support for 2D data, NMR data. So if you've got a COSY spectrum, or if you have HSQC, you can specify in the equations, I'm looking for the area in a particular, for a particular volume, if you like, of a 2D plot, and you can take that and you can integrate that into your analysis. And this is I want to draw your attention to a very nice paper by Patrick Giordano in Med Chem, and Patrick will also be giving a seminar on how to actually do this, how to do 2D quantification at SMASH if you happen to be going later this year. The last big bullet point on these is something that I'm, again, not going to speak about a lot today, but we'll do so in Webinar 2, which is a proprietary algorithm of ours which is called peak pattern recognition. And what this does is to look for a particular peak pattern. So if you say, well, I've got a doublet with these particular coupling constants and at this chemical shift, what it'll do is it'll sort through all the little peaks in your spectrum and try its best to find the 4 peaks that correspond to that. So this is a proprietary algorithm that I'm going to leave largely untouched today, but it does address this whole issue of how do you get over signal overlap in cases where you've got complex spectra. Okay, let's go look at some demos now. So I've got 5 of these for you today. So the first of these is going to be a simple mole percentage of 2 components, and that's a very simple example. Then I'm going to look at the concentration of a drug mixture, some edible oil oleic acid determinations, classical NMR purity determination, and finally a slightly more challenging one where I'm looking at a tissue extract and trying to determine the concentrations of the various amino acids in there. So the first of these is interesting because there's been a recent statement from Med Chem where they basically say that if you want to determine compound purities, they really would like you to use quantification using proton NMR spectroscopy. Okay, so I think this applies, in my mind at least, this applies not only to journals like Med Chem, but I think it really ought to apply to any journal, any organic chemistry journal. And I've seen papers in JOC and lots of others where the people have chosen to use purity by NMR as a way in which to specify the purity of the compounds that they've isolated and produced. Now, along with this editorial is a very nice perspective paper by Pauli's group, Guido Pauli, and this is the reference to it over here, and it's in the same journal issue, and I noticed that there's some supporting information here, and amongst the SI you'll find some Mnova files which you can use for to try these out. And in fact, I'm going to use them today. I'm going to use 2 of them today. So 2 of my data sets come exactly from this paper without, I've just lifted them straight off and used them straight away. Okay, let's dive in now. So the first example is going to be this simple mole percentage of 2 components. So if you buy quercetin, it comes with a known impurity, camphorol, and so it's this des-hydroxy material over here. And the way in which you determine the purity of the quercetin is to say, well, it's this here, which is the mass, if you like, of quercetin divided by the mass of the 2 of them times 100. So mole ratio, that's simple. Let's have a look how it works. That's obviously not the right spectrum, is it? Okay, here we go. Here's the spectrum of quercetin with the camphorol impurity. That's taken from Paulie's article. And as you can see, that a lot of these have got a major peak and a minor peak and so on and so forth, major, minor. But there are 2 peaks here where one corresponds to the impurity and the other one corresponds to the main material, the target material quercetin. Okay, so let's go ahead and analyze this. So how would you do this using SMA? Okay, so let's start it. And here's the first screen that you see. And what we have at the top here in this particular tab are all the bits of information that are required to do this analysis. So I've got these are the particular experiments that I have in my particular library at this point in time. And there's all sorts of ones here that I'm not going to use today and don't really matter. But for this particular analysis, I need to select that one over there, quercetin camphorol mixture analysis. And you see a little description of it at the bottom there that I wrote. I'm not going to talk about the way that I designed the experiment. It is easy, but this will come this will come a bit later. Now, if you do need to specify certain numbers for the particular analysis, weights and reference weights and so on, those can and should be done here. These will be sample-specific stuff. And what you have in the bottom section here under metadata is an area where you can specify things, metadata relating to the sample, so who the customer might be or the standard operating procedure that you're following or whatever. You can pop those in there, and those will appear in the results. So we have some settings here which you can use to do some customization. I won't talk about that. This libraries button here allows you to manage the libraries as you see, and all I have to do at this point is to click on the Analyze button, and the analysis is done for me according to the particular procedure. Okay, so there's the results. The numbers for the quercetin and camphorol are really bogus numbers, if you like. I can turn them off in terms of reporting. And the numbers that I'm interested in are the purity and the impurity levels. So that's all been determined nicely, and it's all very simple. If I want to review the results, there's quite a few ways to do that. I can do something called smart cuts, which is what that does is to divide the spectrum into the particular regions that were used for quantification, so you can see exactly how I set these up. And you can see later on, one of the examples, I'll show you how these can be managed further. So you can see the camphorol has been defined by those 3 signals, and the quercetin by these 4. The reference one doesn't matter. Okay, and I've obviously taken averages of these to make it meaningful. Okay, that's example number 1. Just have a quick look at my notes, see if I'm forgetting anything. Yeah, okay, so what I'll do is I'll just pop a quick report onto the page. So you'll see that in the bottom right here you have a number of things that you can click on. I'm going to click on the settings. I'm going to say paste the report in Mnova, and if I click on report, then you'll see that some information has been pasted onto the page. make that a wee bit bigger for you. Yeah. So that's the results. That's the synopsis of the results there posted on the page, and you could of course make a PDF of this or whatever you want to do, or save this away. If you were to save this away, all the SMA analysis type information will be saved with the Mnova file. That's really important when it comes to doing batch and in-time SMA analysis. It's all saved away. Okay, let's look at our second example now. This is one where we have an over-the-counter drug product called aspirin C. And this has got 5 components: ASA, salicylic acid, ascorbic, citric, and acetic acids. And I'm using TSP that's been added to the sample as an internal reference. And so the type of analysis I'm going to do is this classic equation of concentration is equal to conversion factor times the intervals divided by the number of nuclei. So this is an absolute classic. So let's have a look at the data now. Here we go. So here's a spectrum of aspirin C in D2O. There's a presat's been used to remove most of the water peak, and there's a bit of a residual nasty lump there, which I've made a blind region around just because I'm a bit fussy about these things. I've done the peak picking already. So to do the SMA analysis, all I have to do is to come back here, and I need to choose aspirin C as the experiment. So I've defined this experiment behind the scenes, and it's the only thing that I need to specify in this particular case is the reference concentration. So that's the concentration of the TSP peak. Okay, so let's do the analysis by clicking on Analyze. There we go. And I can reorder these. I can look at the first of these by double-clicking on the row, and it'll bring that into the screen here. I can look at the second. I can cycle through these. I'm now showing the ascorbic acid. I'm now showing salicylic acid, and so on down the list. Now, what I'd like to draw your attention to in this case is a little bit of around alerts. So I didn't have these showing, but you can see that in the alerts box I've got a few things that have been popped up. So it's telling me that the J's for the multiplet of citric acid is not as expected, and the multiplicity is a doublet and was expected to be a doublet. Furthermore, you can see that the citric acid is colored red, and that's again a clue to say that there's something wrong with citric acid. So if I double click on that, it brings it into foreground, and what I'm showing you now is the whole big workflow idea of SMAs. The idea is that SMA is run, you're presented with particular alerts if you wish. You're quickly taken to where these problems may occur in the spectrum. You can fix them, and then you can reanalyze, and you can go through these cycles as many times as you have to or need to go, and then you're done and you can report. So what's happened here? Well, I've purposely set the 2 doublets of citric acid, the integral width, to cover the 2 doublets rather than just 1 doublet, which is what I really want to do. So all I have to do to correct this, I have to just drag this over just to select one of the doublets. You'll see that the citric acid definition now shows as a doublet. And if I click on Update, it's going to recalculate the values, and citric acid, as you see, now comes out without an alert, and I get a color for it other than red, showing me that this is correctly analyzed now. Okay, this is an important point. It's the whole workflow. I've shown it in a very simple example, a contrived example, if you like. But hopefully it gives you an idea of the way in which you can sort of work your way. You can start with a pretty decent analysis and work your way through and quickly get to an answer that you like. Okay, what have we got here? Right, so we've spoken about aspirin C. And we've spoken about the SMA workflow, where it's thrown out the problem of the citric acid, and I went and corrected it manually, and I recalculated it, and then no alerts were thrown, and so I was happy. Okay, so the third example is very different. Here we have, this is very commonly done. I'm looking at various oleic acids in extra virgin olive oil. So this is an analysis that's done very frequently, really. NMR is a very good tool for looking at oleic acids. And all I'm going to do here is I'm going to follow a particular literature reference, which I'll show you in a second. And I've copied a little bit out of the reference here to show you that there is some, what's required to do this analysis is to simply divide the spectrum into regions and determine the area of each of those regions. And these are the A's and the B's, the C's and D's specified in the paper. And then if you want to work out the percentage of linoleic acid or linolenic acid and so on and so forth, then you simply apply these equations, and these have been validated in the paper. So let's see how this works in real life. It's very easy. So let's take that away, bring up the spectrum of olive oil in chloroform, and I've already done the peak picking. So SMA again, I'm going to clear the table because we're doing something new. I'm going to go to the analysis data tab, and now I need to bring up a new experiment, which is vegetable oil composition. Okay, and you can see there's a little note here to say that it's following this particular paper, which is one that I showed you a little bit of. And again, I don't have to give it any new data. Let me clear the alerts here because you can see if there's anything new. And if I click on Analyze, you can see that it's gone through and divided the spectrum into these 10 regions and determined the area for each of those. And using those and the equations which I showed you a second ago, which I've hand-coded in very easily, it's worked out the particular percentages all the way along. Okay, very easy, which I can report and so on and so forth. Okay, that was a really quick one. So now this one I want to spend a little bit more time on because it's an important one. So many of us do NMR purity determinations, and this is a hugely important way in which to determine purity. And it's a number of ways of doing this, but one of the common ways is that which involves what's called a co-dissolved certified reference material, CRM. So the way this is done experimentally is that you weigh out a certain amount of your compound of interest, in this case it's catechin, and then you weigh out a certain amount of your CRM, which DMSO2 was chosen, and then you record the NMR spectrum, and then you apply this particular little equation over here, which is just a bunch of ratios really, and you can work out the percentage purity of the catechin, your compound of interest, if you know the purity of your reference material. So these CRMs are important. You can buy them from a number of companies. I won't mention names, but big companies that you're aware of for chemicals sell CRMs with specified purity levels and so on and so forth. And there's many government agencies and so on that worry about these hugely. And so it's a very well underpinned area in which to work, and using NMR in this way to determine purities, which was really kind of the message that I showed you on that slide from the editors of Med Chem. This is really a very sensible way to go about determining purities. And if you're working certainly in the pharmaceutical industry, you'll find that this is used possibly universally. I can't see why it shouldn't be. I certainly used it millions of times. So the example I'm using is again taken out of Paulie's paper from Med Chem, and let's take a look at the data. So I've got the data over here. See a spectrum over there. It's clear the table, clear the decks. Let's go to analysis and pull up the appropriate table. So in this case, we need a little bit more data. We need to put the weight of, or the mass of the compound that was weighed into the tube, the weight of the reference material, some molecular weights need to be specified. Oh, they're in the equations. Yeah, that's okay. And those can either be entered here, or if you look at the title, you'll see that this RW and the value is there, and the SW and the value is there. And if I delete these, I can show you that if I click on the read parameters, it'll fill those in from the title file or the text file. So you can put these sample-specific numbers into that file to give SMA a hand. And in fact, this is very, very important if you're doing batch processing or real-time SMA. You have to do it this way. Okay, I've got those masses in there. That's all I need to do. I don't need that today. This is telling me a little bit about what the analysis is, and I can again click on Analyze. And it's not much of an answer to show you. That's just it, really. Let's take a look at the smart cuts. So what I've done in this case, I've chosen the particular peaks that you choose is really a bit up to you, and the limits are up to you. So for the CRM, the DMSO2, I've chosen limits like this, although you could make them bigger if you want to include the carbon satellites, and then update the number. It'll change slightly. And so on and so forth. You'd have to do that for the analyte signals as well for it to be valid, so I'd have to do that here. And can't see it for this one. Okay, so that's the problem with carbon satellites. So I've chosen these two protons, number 11 on the structure, for my particular analysis, but there's nothing to stop you from choosing any of the peaks in the spectrum. I wouldn't use the labile protons personally. I never trust the integrations. I think they very frequently under-integrate, so I just don't like them. So let me show you those. So I've got all these peaks here of 9 or so, which are the OHs, and I wouldn't use those. There's lots of other nice clean peaks to use. And I've chosen, I like to use a methylene group because their relaxation should be nice and slow, and so they should give accurate integrals. And they do have the same values, which is good. There's a whole statistical element that you can use if you're using averages, and I'm not going to talk about that in detail today, but I will go into it in the second webinar. Okay, so that's the purity of catechin as determined in this experiment. It's that simple. I have to say that the way in which I've done this particular analysis is specific for catechin. So you can't just suddenly throw in a brand new compound Y that's not related to this, that's got peaks in completely different places, and run the catechin experiment against it. You've got to customize it for the other compound. Okay, but if you're repetitively measuring catechin in a particular way and you'd like to do it the exact same way every time, then this would be a very, very quick way of doing it. Okay? Right. Now, I just wanted to put a quick plug in here for version 1.1 of SMA, which I can show you in private if you wish. It's beta software, so it's not really ready for release. But what we'll be doing in version 1.1, which ought to come out in springtime, I think, is improving a lot the way in which we deal with multiple peaks that are used, or more than one multiplet that's used to define a particular compound. We're improving the ease of generating equations, the stuff I'll be showing you in Webinar 2. And there's quite a lot of stuff in there which basically takes some of the sting out of SMA at the moment. And I hope you like that too. So the whole aspects of statistics will be handled in a much neater way. Okay, that's the end of my purity example, and I hope that resonated with you, and you could see yourself using that. Okay, so I'm on to my last example now, which is a tissue extract. So clear the table again. Let me go to my tissue extract experiment, and I don't know if I have parameters. So what I'm doing in this experiment is I'm using the TSP peak at 0 to determine the concentration conversion factor. So this is the good old classical way of doing things. I'm using this equation yet again. So I'm using the, as I say, the TSP peak of known concentration. I know that's 10 millimolar, and I'm measuring those in the spectrum, and from that I'm determining the CCF, and then I'm determining the concentration of each of the components in the mixture using this equation with the determined CCF inserted in there. Okay, so this one's a bit more tricky, the spectrum's a bit more tricky, and I'm sure some of you might argue as to which peaks I've chosen, and it's not really a validated procedure, so I ask you to give me a little bit of slack on this one. It's really to make a point more than to provide you with a rock-solid analysis. But if I go through and I analyze this, so in this case it's doing the peak picking as well, which will take a minute because it's a complicated old spectrum. There you go. And there you can see it filling in the table. So let's drop this down a wee bit. You can see that it's used the DSS, I guess with DSS, not TSP, for the reference. That's that over there. And we can look at all of these. We can go to lost the table. It's hiding behind the spectrum here. Let me find it. Ah, there it is. Okie dokie. Right, so there's the results. So I've got these particular metabolites and mainly amino acids that I've determined macromolar quantities of, and there they are. And if I want to look through them, I can double click on that one, and it shows me how the alanine, which alanine peaks were used to assay for alanine there. The formate was that particular singlet. Lysine is a doublet over there, and so on and so forth. Notice that I'm using the GSD peak picking in this instance because I've got so many overlapping peaks that it would be foolhardy to integrate regions in this case. So GSD peak picking is the way forward. Okay, that's my last example. Let's go back to the PowerPoint presentation and see what we have here. So I wanted to speak about reporting a little bit. So what can you put inside reports? You can put SMA results, input values, so the masses and so on and so forth, any metadata that you happen to add, and you can also specify instrument parameters, so that's useful too. In terms of the way in which you actually do your reporting, you can do this on the spectrum, which is something I showed you. Or you can ask it to write an XML file, and I'll show you an example of that here. It's an XML file that's been written, and of course XML is a hugely popular and useful way in which to further elaborate the information here. So if you wanted to convert this XML into some sort of web page that shows the results with your company logo and so on and so forth, then that's something that can be done quite easily in code. And I'm sure some of you will be familiar with style sheets and so on and so forth, but you need to understand to do that. But this is a very nice way to store the data. It makes it convenient too for uploading to databases. So if you have a corporate database where you keep all this type of information, where you say, okay, I've done this particular analysis on quercetin and I've got a result of 83.5%. Got a result there of 83.5% for that, and impurity level was that. You can quite easily transfer that into your database, and we have collaborators who do that. Okay, so why is it letting me go down? Hold on. Right, so I'm at the end of things for today, really. I hope that the conclusions that I've put on this slide make sense to you, and that you agree that I've shown you a powerful and flexible tool for method analysis using NMR data. We have provide full user control over every aspect of the analysis, whether it's the design of the experiment. You have to take my word on that one today and come back to the second webinar to see that in action. Whether it's that or whether it's the inspection of the particular analysis and touching up particular regions and assignments to make sure that things are absolutely perfect. There's a powerful experimental design concept that's made available to you. This is this workflow that I spoke about and showed you that ensures confidence in the correct analysis. So once you put the numbers down and you publish your report, the hope is that because you've gone through and done a little bit of triage of the data in areas where the software is telling you there's maybe something wrong, this should give you confidence that you're reporting the correct values here. And that's very important. Now, I've only shown you the interactive operation, but showing you the batch and the real-time operation is a very boring demo. It's just lots and lots of the same thing with Mnova files being written, if you like, or XML files, and it just goes on, and then, if you like, you can go back and review those at a later time. So, I thank you for your time today. I'm going to put a little bit of a plug for the second webinar. In this, I'm going to talk a little bit about SMA 1.1, this new version that's going to have expanded capability. I'm going to describe how to manage your experiments in libraries. I'm going to show you how to create your own experiments, and this is going to be a large proportion of the webinar. Database usage, so you can have your particular constituents inside an Mnova database, and you can import those very readily and easily into a particular experiment. I'll show you that. I'll describe the peak pattern recognition algorithm to you and how that works. I'll show you how you can use stats inside your analysis, and I may show you some stuff on batch and real-time usage. As I say, it's a pretty boring demo, but it does work. Okay, so I thank you very much indeed for your time today, and I see I have 10 minutes left on the hour, and if there are any questions, I'll be happy to take those. Let me take a quick look-see. Are there any questions?